All right, team. It's Andrew Voss here, and we've got a great example of the forces acting on the Falcon 9 rocket during the first return of astronauts to the International Space Station by SpaceX with the Crew Demo 2 launch. So we're going to be examining the Newtonian physics going on in this rocket flight. So let's watch.
15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Ignition. Lift off.
All right, so see Falcon 9 here lifting off from the pad. Let's see what forces are acting on the rocket. So we are going to use some arrows. So at liftoff, the rocket is moving off the pad. Initially, its velocity is 0 and its altitude is 0. And it sits on the pad under just 1g of Earth gravity, with all that force being reacted by the launch pad and the ground. But when the engines turn on, the vehicle begins to move. So the engines turning on provides a force here, which is the thrust force. The Falcon 9 produces approximately 1.7 million pounds of thrust at liftoff. Now, the force from gravity is due to the mass of Falcon 9, and that is pulling it down towards the Earth here. So that arrow is the gravity. So we have here thrust 1.7 million, and here weight equals 1.2 million. So the thrust is greater than the weight, and the rocket moves off the pad, accelerating in the upward direction. So how would we determine how much that acceleration is? Well, if I make a new text over here, we have force equals mass times acceleration. Really, it's the sum of the forces. So the sum of the forces, since they're opposing each other, is 1.7 minus 1.5 million pounds, minus 1.2 million pounds, or 500,000 pounds. Then the mass is 1.2 million pounds of mass, as we can see here by the weight. And that's multiplied by the acceleration. So we want to determine what the acceleration is. So acceleration is equal to 0.5 divided by 1.2 million equals about 0.4 Gs. Now in real life, to make the liftoff less violent and dynamic for the vehicle and the astronauts, the engines are reduced from their full 1.7 million pounds of thrust, and they are throttled down to lift off at something closer to 0.1 to 0.3 Gs, depending on the mission. Now, as you remember, at liftoff, the velocity is 0. What does that tell us about the aerodynamic forces? That tells us that there are no drag forces at liftoff from the motion of the vehicle opposing its motion, because the velocity has not left the value of 0 yet. So the drag force will be coming as the vehicle starts to move faster and faster, and the velocity will increase as the acceleration persists and the thrust continues to dominate the weight, because the velocity is the change in, or the velocity is the area under the curve of the acceleration over time, which we'll talk about more later. So let's go to a different part of the flight.
Falcon 9 and Crew Dragon, go NASA, go SpaceX, Godspeed, Bob and Doug.
Look at it go.
America has launched. And so rises a new.
So now as the mission continues on a few seconds later, the velocity is continuing to increase faster and faster. The thrust is persistent and maybe increasing a little bit as the liftoff phase is over and they throttle up the engines. The mass and the weight are decreasing rapidly as the vehicle burns through rocket propellants. The rocket propellants, the fuels, make up most of the weight of Falcon 9. And so, as the engines fire at their full power, the weight of the Falcon 9 decreases substantially, as does the mass. This allows the acceleration to increase.
Era of American spaceflight, and with it the ambitions of a new generation continuing the dream. 20 seconds into flight stage.
Watch the speed here in the bottom left, or the velocity, continue to increase more and more. Also, the altitude, or the position, continues to increase as it approaches 1 kilometer in the sky now.
Propulsion is nominal.
Let's pause here to examine the forces again on the rocket. So now the rocket is about 30 seconds into flight, going 420 kilometers per hour. We still have the same thrust coming up from 9 Merlin engines, approximately 1.7 million pounds of thrust when all of them are firing. We have the weight of the rocket acting at the center of mass, pulling it back down towards the Earth. And we have a new force, a third one resisting the motion that is opposite to the direction of motion of the rocket, which is the drag. Now that drag is new because it was not at liftoff, because the rocket is now moving and moving fast through the atmosphere. So we have drag, we have weight, and we have thrust. So how would we calculate the acceleration of the rocket now? Well, the sum of the forces would be the thrust minus the 2 negative forces, the drag and the weight. So F equals thrust minus drag minus weight, and F equals mass times acceleration. So thrust minus drag minus weight equals mass times acceleration. So in this case, the thrust has maybe gone up a little bit since liftoff. The drag is new and high because the rocket is moving fast through the atmosphere, and the drag increases exponentially with velocity. The weight has decreased since liftoff because of all the propellants the rocket has burned. It will be proportional to the burn rate of the fuels times how much time the rocket has flown for. The same thing is true for the mass. Now, the weight and the mass are not exactly the same, but on Earth's surface, if you just multiply the mass times the gravitational constant of 1g, you'll have the weight, and you can convert between the two, meaning you can use the same variable, which is the mass of the Falcon 9, to represent both the mass and the weight, as long as you have correct units. Then finally, the only unknown remaining would be the acceleration. So to calculate the drag, which is the new force, you would need to know the atmospheric density at this point in the altitude of 1.4 kilometers. You would need to know the velocity, which we can see here from the webcast is 420 kilometers per hour. You would need to pick a reference area for the Falcon 9, which is most often the cross-sectional area of the rocket. And you would need to know the coefficient of drag for the rocket, which, if you recall, is possible to calculate from test or analysis, but is not the most simple of calculations. So to give you an answer, at this point in the launch, the acceleration is increasing and continues to increase until stage separation. So after lifting off at something like 0.2 or 0.3 Gs, it continues to increase and increase until 3 to 4 Gs at main engine cutoff. So the drag, because of the increasing velocity, will continue to increase as well as the rocket goes faster and faster. This all culminates on a point called max Q, or when the aerodynamic pressure is the highest. That's from the velocity times the velocity squared times the air density being at its maximum point. Let's clear the screen and wait for max Q and then complete this summary.
T plus 30 seconds into this historic mission. Flying crew on board Dragon and Falcon 9, and look at them go.
Falcon power telemetry nominal.
M1D throttle down.
We're throttling down to get ready for the period of maximum dynamic pressure. We're in the throttle bucket. Reports say all systems are go.
Vehicle is supersonic.
So the vehicle has just crossed the speed of sound, and we're right in the phase here of maximum aerodynamic pressure, which usually occurs right around Mach 1, the speed of sound, or vehicle transonic, as the vehicle is going from subsonic, slower than the speed of sound, to supersonic, faster than the speed of sound. So here we have the speed at 1,080 kilometers per hour, and it is now nearly 10 kilometers in the atmosphere. This is the point where the atmosphere starts to get thin faster than the velocity of the rocket increases, so that actually the drag forces and thus the aerodynamic stresses on the rocket are getting lower throughout the launch. This is a critical juncture in all rocket launches because the vehicle experiences very high stresses and huge amount of resistance on its path to completion of the mission.
We've exceeded Mach 1 on the Falcon 9.
Thanks for watching, and go SpaceX, go Dragon, go Bob and Doug on their mission to outer space.